Okay. Can you hear me okay? Okay, so it's a pleasure to give experimental highlights of ICHEP 12. Actually, this year, there's a few special anniversaries, it turns out. 1964, on July 10th, is tomorrow, 50 years ago, Cronin and Fitch et al. Submitted a paper announcing the discovery of a CP violation in the weak decays of neutral kaons. So that's great. Last 5 decades of CP violation effort done in our community. In the same year, turns out in January 1964, Gelman proposed that quark model and published his paper. So that's another 50 years in 50th anniversary. And of course, CERN, the 60th anniversary, we have been celebrating throughout this conference. So I thought about what ICHEP 2014 means. Usually, to my mind, sort of we look back from the last ICHEP, what we have done, for example, what kind of physics results we have published. That's one very important primary goal, and we present those results here. If roughly add all the number of the publications from talking to the spokespeople, etc., it's much more than 500 experimental papers, and that's incredible, the amount of work and success and achievements. While we are publishing data and physics, also we have been doing a lot of work on advancing our capabilities, and starting with the near-term future, for example. So we have been upgrading experiments and accelerators. And in some cases, we are brand new detectors are being built. We develop technologies, all kinds of computing accelerator and detector, and also analysis tools as well. And also, we have been also working very closely with our theory colleagues, because any physics results mean that there are strong, there's a collaboration with the theorists, because we are using their the calculations and theory and so models and so on and so forth. So that's one second item. And of course, another thing that we have been doing quite last couple of years that we have discussed a lot on Monday evening was this planning our long-term future. So, so that's another thing that our community does. And I'm also very glad that actually this conference paid a lot of focus and attention on outreach and physics, and that's something that we always can do more and better. So let me start with 2 highlights from last ICHEP at Melbourne. One, of course, is the discovery of then it's called a Higgs-like boson from Atlas and CMS, beautiful results, and that led to 2013 Nobel Prize in Physics. England and the Higgs got Nobel Prize. So that one big highlight. Another one was a theta 1,3. This is last mixing angle in neutrino sector. Until then, there was a limit by show around sine square to theta 1,3, about 0.1-ish, and this is as large as it can get below that the limit by double show. And that's beautiful. First results by Diabe, immediately followed by Reno. This is, of course, already quite accurate measurements. So looking at all these particles that we have discovered, and now Higgs is the last one, so I was just looking at and making this plot, and starting from electrons to all the way top quark. Here, yellows are these neutrinos. And so it took about more than a century, and gauge sector, W's and Z and gluons around here, finally Higgs boson. So, so this really completes the Higgs standard model. Now, of course, the question is that, as we know, that Higgs standard model is not the complete theory of particle physics, and there are still many questions to be answered. Some come from theoretical arguments, and some are really experimental. The observations already told us that standard model does not work. So there are many questions remain, and we need new physics to answer these questions. So if you do our physics research in particle physics, we often testing our standard model for fermionic sector that include the charged the fermions and neutral neutrino sector, and the gauge sector, and now the Higgs sector by testing standard model as precisely as possible. We're trying to find the hints. And also, of course, we look for new physics, the models and particles predicted by new physics models as well. But in addition, we have a baryonic asymmetry. The universe is dominated by matter. That question already observed, and we have to go after that. And dark matter and dark energy, these don't belong in the standard model, and we are looking for the evidence or associated particles for that. So going back to, again, Higgs discovery in theta 1-3, we were quite lucky, in fact. Nature has been very kind to us. If you look at the 125 GeV Higgs, here there are all different branching ratios for different mass. And 125 GeV, as you can see that there are quite many the branching ratios actually are accessible by the, for example, LSC. So we can study Higgs to many kinds of particles and their interactions. So that's a quite fortunate situation. Theta 1-3 is a similar situation. This chart shows you the probability of muon neutrino oscillate to electron neutrino, and this is the anti-neutrino, the word. If this angle is B, then mass hierarchy, normal and the inverted hierarchy, they are quite separated out. And also the contour, which is phase CP violating phase phi from 0 to 2 pi going around, that's bigger. So that means that you can disentangle this normal hierarchy and inverted hierarchy, and also measuring the angle CP phase much easier. But if it goes very, very small, for example, theta 1-3 is 0, there's no hope of seeing the CP violation. So we are quite lucky that the angle is as big as it can get. And with that Higgs mass and theta 1-3 value, these are very, very important, help us, in fact, guide what our directions of future will be. In fact, all the world community, Asian community and European and American community, sometimes a region or sometimes countries, we have gone through a planning exercise the last couple of years, and we all came up with a consensus that particle physics is global. And also that if you look at each region, what their vision is, we are all kind of very similar. Firstly, we all join the partnerships in global facilities hosted somewhere else. Like a good example is LSC. Another example might be future high energy colliders. These are global scales. Doesn't matter where they are, we'll all join partnerships. At the same time, each region may not be global scale, but substantial and world-class facilities, so that this can support the entire world community about that specific the areas of interest. So combining both, these are quite important to be really this global, the world community's goal, and that is the global vision that we sort of agreeing on that. As you heard also Monday discussion, I think we have consensus on that. I really hope that in the future we continue our strategic planning together in the global context. So science drivers, I use these science drivers recently reported by the United States, the Community Snow Mass Activities and P5 panel. This as one example and very recent, therefore I'm going to use that as guidance of my presentation. So there are 5 intertwined scientific drivers, including use the Higgs boson as a new tool for discovery, pursue the physics associated with the neutrino mass, identify the new physics of dark matter, understand cosmic acceleration, dark energy and inflation, explore the unknown, new particles, interactions, and physics principles. So actually there are many Nobel Prizes associated with it. We know that the 2013 with the Higgs, and neutrino 2002, acceleration of the rate of the universe, the expansion, 2011, and also the 2004 and 2008 associated the last item. So of course, dark matter, if you discover hopefully 201 something X, hopefully, then I'm sure that the big recognition will be there. And other discoveries, of course, around here also will get good recognition from the community, I'm sure. So addressing these questions, first of all, these questions are quite compelling, but it's very difficult and intertwined. Therefore, we need multiple approaches. And this is only possible because there are a lot of advances, thanks to advances from the accelerator and detector technology and computer technology that we heard a lot earlier today. So these approaches include high energy colliders, so various kind of neutrino experiments, cosmic survey, dark matter experiments, precision measurement, rare processes, and all that, only combining together, we can really get to answer all those questions. So let me start with Higgs. We started 2 years ago discovery of a Higgs-like particle to now. We measure properties of Higgs quite precisely in some cases, and we started using Higgs as a new tool for discovering something else. On July 4th, we had a very nice celebration, the second anniversary of the Higgs discovery. Juan is extremely happy, even though he's very tired, I'm sure. And we had two spokespeople who have been serving all of us. They are very busy, but I'm sure that they are very happy to serve all of us for this very nice occasion. So came to this conference, I realized it's not called Higgs physics, it said BH physics. And it took me 1 second and what BH meant. In 2016, ICHEP will be in Chicago in the United States. 2010, American Physical Society gave an award. It's called a very prestigious award called Sakurai Award to 6 theorists for their work on like Higgs mechanism. So there are not only these 3, but Goralnik, Hagen, and Kibble are also included. So 6 people get it. And since now ICHEP will be in US, maybe we have to call something like that, I don't know. It might be hard to even pronounce. So electroweak symmetry breaking sector or Higgs sector, there are many open questions. It was very well summarized by Christoph. Most of them I'm sure that we are very familiar with. Also, actually, good to see that connecting to hidden world or matter-antimatter symmetry and inflationary expansion of universe. So Higgs is quite something might be to do with that. But I also learned something else, what Higgs is about. That is, can it ensure that Brazil will win the World Cup? I never thought that this is related to Higgs, but you always learn something. Okay, so the results about Higgs, of course, it's primarily coming from LSC, but there are some results also came from Tevatron. By the way, this is a PP bar, not PP. So this was the 2 years ago, Higgs to gamma gamma and Higgs to jet jet discovery time. Now look very similar now, more statistics, except the scale is different and much larger. You'll see that each experiment now observation is a 7.1 sigma, 3.2 sigma, 6.6, 6.8 sigma. So you'll see that each channel, each experiment really could declare discovery. So that's the difference between then and now. Not only that, it was a counting experiment then, but now we have more data and we can really deep look inside. We can make a differential cross-section. This is an example of a PT of 2 photons for this sample. You may ask what's going on, why it's higher than expected. Of course, we need more data to understand whether there's something really there or this is a statistical fluctuation. Now, it was the boson, Higgs decaying to boson for discovery, but we have to also find out whether Higgs really coupled to fermions, because in the end, Higgs has to give a mass to the fermions. So this is new results from CMS and Atlas. You'll see that Higgs to tau tau, 3.2 sigma, Higgs to BB, 2.1 sigma, Higgs to tau tau, 4.1 sigma. All together, it's more than 5 sigma discovery. And I just want to compare that earlier fermion tevatrons, also the hint at the level of 3 sigma in the fermions. So together, including even TTH coupling, they are very nicely aligned in this curve. The agreeing with the standard model as a function of their mass and has to be this line. Even within 1 sigma, everything aligned with that. We can also turn around and ask whether there's any constraint we can make on the new physics. By the way, these are all strange characters. There's incompatibility between this Mac to this PC, so sorry about that. So looking at this possibility of new physics through loop diagrams, we can also answer those questions. But looks like all agreeing with the standard model up to 2 sigma. So bottom line now is all seem to be consistent with the standard model. For Higgs mass, from ZZ to 4 lepton channel and 2 photon channel, look at this precise measurement, CMS and Atlas. They are very close to each other in central value. Uncertainty is about 0.3, 0.4 level. So it's already together at a 0.2% level of accuracy. This is a very, very precise. Something that we usually don't see in this kind of accurate precision measurement is how much work behind it. I mean, to get to this point, we have an incredible amount of calibration work for momentum scale to energy scale. So tons of work it has been done to make this happen. So now Higgs is 0 plus, this is the spin parity. The Atlas CMS and D0 all checked whether 0 plus is favored or not, and the answer is yes, and they're still, so therefore consistent with standard model. There's one thing very interesting came very recently is about width of Higgs. Higgs width is 4 MeV, and conventional method is impossible because we are going to look at the invariant mass distribution, and detector resolution is up to a few GeV. So it's pretty much impossible. However, our brilliant theories came up with a new idea shown here. This is, of course, a bright beginner, the peak of Higgs at 125 GeV. But high mass range or high energy range, Higgs becomes more propagator. So you'll end up getting the cross section through Higgs and continuum. That's really sensitive to how much what the Higgs width is. So by making the ratio of here to there, we can extract the Higgs width, and that's what's done. And both CMS and Atlas looked at that. The conclusion is that the width is about less than 20 or 25 MeV at 95% confidence level. One thing, however, though, there are a lot of discussion going on, collaborations and the theorists, that what kind of assumptions are made. For example, coupling, Higgs coupling to the particles at very high energy to 125 GeV, not necessarily same because the couplings run, but here we just assume simply they are the same. So there are a number of assumptions going in there, but we'll have a better understanding in the future. This made me think actually, one thing very interests me for this case is that often data makes people or scientists smarter. Before LSC start taking data, I don't think this kind of idea was known, but seeing the data and all that, and we can get much better physics out of it because we have new ideas going into all this analysis and techniques and procedures. One more thing about Higgs, the weak electroweak symmetry breaking, all this WW scattering, cross-section has a very bad behavior at large energy, and Higgs has come in and canceled that to rescue that bad behavior. And Higgs is necessary for that, and we have to test whether that's the case or not. Experimentally, it's done with the 2W plus 2 jets, and this is Atlas results of really that 3.6 sigma significant way it's necessary, so that's agreeing with the standard model, and CDMS has at the level of 2 sigma significance. So they're still agreeing with the standard model. Now Higgs is being used as a new tool for discovery for the individual Higgs channel, for dark matter search, or flavor-changing neutral current, or any type Higgs of the resonances, or et cetera, Higgs, Chide Higgs, or SUSY Higgs. One thing, quite interesting thing is that dark matter search using this Higgs as tool. Here's a cross-section versus a mass, and you'll see the CMS eliminated this area. that can be compared with the direct dark matter search, which is excluded here. So what the main point here is that these approaches are quite complementary to each other. So moving to gauge sector, a lot of experiments come from all over the world, the US to Europe and Asia. So these are many the experiments contributed in this sector. Starting with the Atlas and CMS, the standard model cross-section. So all the way start from total cross-section 10 to the 11 picobond to there are many different channels, standard model channels, and all the way down to WWZ channel, which is about 10 to the minus 3. So 14 orders of magnitude difference from here to there. Similarly, CMS also made beautiful measurements. Again, each point is a 1 point, but behind the 1 point, there are a lot of the effort going in there, both experimental side and the theoretical side. So far, everything agreeing with the distant model cross-sections. I want to point out again that this is a tribute to a large amount of work done by collaborations and the theory colleagues. So one of the points there are this vector boson fusion production showing this 2 vector boson fusion to make a Z plus 2 quarks. That is, of course, needed in standard model. So both CMS and Atlas have done a wonderful job on that. This plot shows you the number of events as a function of a digest mass. Data points are black. And red one is what if we don't include this diagram. Certainly that doesn't agree with the data. So if we then include that, and that gives a good agreement. So again, kind of again showing that, demonstrating that this is needed and agreeing with the standard model. Moving to testing QCD, this is another or more than 10 orders of magnitude, a beautiful agreement between data and high order calculations. And alpha sub S from Hera, Tevatron, and LSC, the current, the accuracy is 0.5%. This plot is quite nice because this, first of all, several experiments all put together made this one. And coming from a few GV to TV, beautifully running the alpha sub S is demonstrated there. W plus Z or Z plus Z, also very important measurements for really testing out the sort of the high order corrections and all the models going into the Monte Carlo has good testing whether these corrections are at the right level and models the right level. And again, very, very important measurements done both CMS and Atlas. Pattern distribution functions, we had a many discussion in the talk. Often a number of important measurements, especially precision measurements, or in case very high mass, the high Q-square searches run into this as a high, one of the dominant, the uncertainties, systematic uncertainties. There are more information coming in still from Hera to Tevatron, and actually it was nice to see that LCB also jumped into here and help. Quite importantly, all the gluon PDFs are not very well known, and LSC experiments themselves are the important input to this. So about the tetraquark and pentaquark, we have heard this a lot in the past. So there has been a long history of finding or searching for these exotic hadrons without much conclusive results. Last couple of years, however, there are quite nice, the resonance showed up. Don't look like conventional charmonium, so could be tetraquarks. From BS to experiments, 3 experiments in Bell and LSCB, both showing very nice results on that. So heavy ion collisions, this is can be called as a field of hot and dense QCD matter. The goal is to really understand the quark-gluon, the plasma stage to hadron phase in the early universe. There are quite a bit of the exciting data coming in from LSC. Of course, Alice is the prime, the leader of all this area, but Atlas, CMS, and LSCB also contribute quite a bit, including lead-lead, proton-lead, and proton-proton collisions. Rick has done a very nice beam energy scan, and plan is this with their upgrades, explore characteristics of the phase diagram, which is a quite important area as well. So there are a number of ingredients needed to get to really understanding that area. For example, pinning down the initial condition. This is quite relevant to QCD. Also, their evolution via relativistic viscous hydrodynamics. So maybe this is something quite also good collaboration with the condensed matter folks somehow. Anyhow, so far their data have demonstrated what's going on, and then a lot of nice work has been done to understand these items. And they also have to understand quantitatively energy loss of various flavors. This plot shows you the energy of track and jet at the level of a a few GeV to all the way a couple of hundred GeV. Both all the ALICE and CMS and ATLAS together really demonstrated this significant energy loss. And pattern distribution function here also showing that there's a need of modification there for nuclear PDFs. So a lot of effort and very nice progress being made there. Now moving to neutrinos, there has been a lot of progress made in the last 2 decades after the surprising discoveries made. Of course, there are a lot of measurements done, but a lot of questions also remain. A couple of the example of such questions are we still don't know absolute mass value of neutrino. We don't know whether neutrino mass is anything to do with the Higgs or not. We don't know whether neutrino mass spectrum is like a quark-like, or the other way around. We call that normal and inverted hierarchy. Or we don't know whether there's a CP violation in the neutrino sector. We don't know whether neutrinos are their own antiparticles, or we call marijuana particles. Whether there are additional neutrinos, like sterile neutrinos, or new interactions, so on and so forth. So there are many questions to be answered. And neutrinos are related to everything, SUSY to cosmology, gut, flavor physics, and astrophysics. And also they are everywhere. Sorry, also there's some characters broken because of mismatch of my laptop and this PC. Just showing this plot showing you all different energy, very wide range of neutrino energy, all coming from all over the place, from accelerator-based atmospheric neutrino, cosmic neutrinos, and so on and so forth. The reactor neutrinos, all different energy range, all different distances between the sources to a detector. So really, this is really rich the area of neutrino field. So a couple of the significant experimental examples. Reactor-based neutrino experiments, WSHO in France, and Diabe in China, and Reno in Korea. I already mentioned their early theta 1-3 measurements. I'll show you a bit more later, the recent ones. Both the Diabe and Reno have a very aggressive next generation detector with a larger scale and a longer distance. This is a quite exciting time for them, and we are very happy to see this aggressive approach for the next generation. Accelerator-based neutrinos, this is a T2K from J-Park accelerator to Super K detector, about 300 kilometer. So the T2K made the first theta 1-3 measurements from accelerator-based experiments last year. So there was a very nice result to see. For CERN to opera, this operation of this experiment is ended, but they are still analyzing data. Very recently, they got the first event of mu neutrino to tau neutrino appearance, so it's the oscillation. So they have so far the significance of this oscillation at the 4 sigma level. And for Fermilab to Sudan Mine and Minos Plus, it's still running. And now we add the US add NOVA, the experiment that's 800 kilometer. So about this data taking started, although completion of detector will be just a little bit longer because it's modular, so you can still take data while completing the detector. And then there's a short baseline program at Fermilab called the Microboon. This will start early next year. So this is the sign 1,3, theta 1,3. That's where we were before 2011 to 2012 and 2013 and 2014. So you see that huge progress, and it's quite impressive. The latest measurement from Diabetes shows the error about there, and this is a really good progress made there. Although there's something peculiar thing I'll show you, apparently this does not affect the theta 1,3 value because they are comparing near to far detector. But they've seen in the data from double show at 5 GeV visible energy, 5 GeV renal, and 5 GeV the diabetes. There's something that they have to figure out, and hopefully by next the ICHEP meeting they will have the answer. There are more. The measurements came from T2K. They got the best measurement of theta 2,3 shown here. They can be compared with the MINOS results and Super K results. So overall, very huge improvement in theta 1,3 and theta 2,3. And there's also very interesting hint for CP violating phase from T2K. You see this chi-square is very small here, and here minus 0.5 pi or 1.5 pi. We often have two languages. But nonetheless, this is, if that's the case, this is very lucky. It's a very nice spot to really resolve the mass hierarchy and etc. So far, mass hierarchy area, we don't have much of sensitivity. I mean, much information there or hints. I mentioned that this future experiment, NOVA and microbe, to show you that this is the detector and person. You see that scale, so you see this feel for scale of this detector, and almost complete, but start taking data and see neutrino beams. Microbeam is the near the short baseline experiments using liquid argon TPC, and start taking data from early next year. So moving to the question whether neutrinos are their own antiparticles, or called Majorana particle. There are very, very active these experiments going on, shown here, and also planning for future experiment as well. In terms of sensitivity, this is the level as a function of the largest neutrino mass in EV. And if you go to one order of magnitude more, they'll hit to the inverted scenario of neutrino. That's the case, we'll have some good results then. Otherwise, this will have to hit the normal hierarchy, which will be much tougher. Of course, that also depending on neutrino mass. We heard this morning a beautiful result from ICHEP and Tares on very, very high energy neutrinos, very exciting. They're going after finding out whether there are what sources this neutrino, where these neutrinos from. They don't have any clear significant answers, but we have to wait and see. And supernova neutrinos, we are still waiting. We don't know when it comes, but we are all ready. And here are the list of all the experiments. They are not necessarily constructed or designed for supernova neutrinos, but they will see them. Just this plot shows you the richness of neutrino experiments ongoing and planned. One thing missing in this chart I noticed is ENO. This is India Neutrino Observatory. So this is underground, the 50 kiloton magnetized ion calorimeter detector. I think this will add quite a bit of new knowledge, well, adding our knowledge on neutrinos substantially when it starts operating. So we look forward to this experiment. Moving to dark matter, so its mere existence, of course, implies that our inventory of the basic building blocks of nature is incomplete, and we don't fully understand how we got here and where we are going. And this is a grand challenge for fundamental physics and the astronomy. And there are quite a bit of activities going on to see or to discover dark matter. There are multiple ways of discovering, so-called direct discovery, direct detection, search, meaning that the dark matter interact with your mass detector. So it's a nuclei and dark matter interactions, and then dark matter scattered off, and nuclei just recoiled, and you measure phonons and heats and charge and etc. To detect dark matter. So that's one way. Another way is indirect, so-called indirect detection. It's in the in space. dark matter collide, making two ordinary particles like photons or E plus E minus. Or the third way is called the collider production, like LSC. We can create the dark matter as well. So one interesting thing is that these methods, if you look at the sensitivity, they are complementary to each other. I showed you earlier in CMS results that collider, the program dark matter search, is very sensitive to low dark matter mass, while the direct searches tend to be a high mass. So start with the indirect dark matter searches, all space-based and ground-based programs. We heard a lot about cosmic ray experiments yesterday, and we saw beautiful AMS measurements compared with the previous results, and we really look forward to limits or observations from these experiments in the future. Regarding direct dark matter search, these are the locations of these experiments. By the way, these require underground, so they have to go deep underground to shield, of course, cosmic ray backgrounds. And same underground facility we often use for large long baseline neutrino, accelerator-based neutrino experiments, or neutronless double beta decay. Or, by the way, the large detector for neutrino experiments can be also used for proton decays. So we share this underground facility together. Anyhow, point here is this diversity of all the detectors and locations and technologies, so that there are quite a bit of the vibrant field here. For spin-dependent the measurement, there's a steady progress being made. Spin-independent case, there are first you see there are a lot of more plots, meaning that a lot going on there. This area here, solid line and above are excluded. And these bubbles here, these are sort of hints of dark matter. So you see that there are hints, but they are excluded, and these bubbles show up different places. So there are quite a bit of, you can imagine, debates among the field. Here, another plot, the dotted ones are future prospects with the new proposed detectors. That goes very, very close to the limit. This cosmic neutrino, this background will hit that much. Therefore, going beyond will be extremely hard. So anyway, it's a really vibrant and active area, and really look forward to see something exciting in the near future. So that current situation of dark matter field was very well summarized by Perez speaker Paolo Gondolo last week. He says, the forbidden fruit, confusion of the mind, treason and murder, that which does not kill us makes us stronger. So you can laugh, but I think that's really true, that this the dark matter program, or because of all this various the contradictory issues, and it becomes a very, very strong field and have a much better understanding. Moving to dark matter, there are two periods. One is the inflation. We discussed a lot, so I don't want to touch. Next one is studied very recently and continued today. It could be dark energy, or could be really lack of understanding gravity and require some modification. Nonetheless, this is a big question. So the best experiment that's going on is called the dark energy survey. This is almost a 0.5 gigapixel digital camera. I think this is the best digital camera in the world. Started taking data about 10 months ago, and they finished first season data taking last fall and being processed. They believe that from last year's season and this coming year's season, they'll have some first results on dark energy. So after that, it's much more powerful, the ground-based and space-based projects really probing dark energy is being prepared. Moving to the last item of 5, that the science drivers explore their unknowns. There's new particles. Either you have a direct searches like the LSC, or indirect search via virtual particles. Let me start with the direct searches. Frank, on Monday, he said he has 30 minutes talking about all these new particle searches. It's impossible. I have only a few minutes, so I'm much more impossible. Therefore, I don't know there's a word called much more impossible. But Nonetheless, all I'm going to show is a summary. Again, this is SUSY-related searches at Atlas. Each line, again, remember that's again, it's a really tremendous work behind each number. And you'll see that pretty much all the possible searches are done. The scale is in log and 10 GV to 1 TV. There are some areas of certainly gaps, and there are much more difficult reasons. Similar studies done, searches done, and CMS. This is the 1 TV. Also, similar channels. The difficult channels that happen both cases. This is the exotic searches beyond the SUSY. They also went through all different models. Here the scale is 1 TV here and 10 TV, so 1 to a few TV level. Same thing as the shown CMS results as well. So I'm just quoting the frank summary here. Atlas CMS looked all over the place, very different ways and signatures. Produced resonance, singly produced resonance limits up to 5 TV, and pair produced up to 1.5 TV or so. They looked at everywhere, but they haven't found that there's a place they looked at. Of course, there are possibilities that we miss somewhere. It's always the devil's in the details. So still there are many places left to hide, but there are more powerful accelerators and more powerful detectors. Upgrades are coming up. So the next couple of slides will show you that prospects of the LSC in the future. So this is where we are, picking those difficult SUSY channels. The limits are here. For run 2 at 1314 TV with a 300 inverse femtoband, that becomes that. Further high luminosity upgrade, that becomes that. So you'll see that how much enhancement for each upgrade makes. So now for the virtual or indirect start studies, then here are more flavor, the physics engaged. So question here are why there are 3 families, not different number, why there are so many elementary particles, what are origins of masses and mixings, to why the mixing, the parameter or matrix is so different from neutrinos, CP violation at lepton sector, matter antimatter symmetry, baryon charged lepton violation, etc., etc. Very long list. Here again, there are many experimental programs all over the world that contribute to these questions. I'll start with the high mass to low mass, starting with the top mass. This is a Tevatron last year's results with LHC 7 TV. We are talking about 0.5%, very accurate measurements. The word combination is done this year. Of course, this precision measurements is very relevant for standard model tests and new physics and cosmology implications. There are this new, brand new measurement just came to ICHEP. So this is the current world average done this year. And these are new measurements to CMS, all jet channel, and lepton plus jet channel. You notice that error bars are very similar. So this is another very active area, and there are a lot of progress will be made in the near future. Since I'm talking about top mass, I just want to note that the W mass world average is 15 MeV, and Tevatron alone is 16 MeV. It's dominated by Tevatron. Still not full data is used, so Tevatron expect to have as low as 10 MeV. It will be very, very nice results then. There was a lot of hot topics about the top and TT bar for the backward symmetry, not agreeing with the standard model for a couple of sigma level at Tevatron. So that was a standard model calculation to the early, about half of the total data used. It's a bit high. And the recent one, these numbers with the total data used and different channels also used and make a little bit lower than this value, and the theory value went up. In the end, they look quite agreeing each other. LSC, we are not measuring the same quantity, but related measurements can be compared with the standard model. There's no surprise, it's very agreeing with the standard model. So moving to dimuons, this is very impressive plots of LSCB and CMS and Atlas as functional mass. You'll see that, first of all, number is huge. Secondly, all the peaks or the resonances at very low mass to high mass, these are very, very crucial to calibrate the detector, but also they are using them for improving all various models of background and also physics search as well. one important one is the B sub S decaying to mu mu. This is very sensitive to new physics, especially SUSY when time beta is large. So this has been going on last 3 decades. This plot shows that log plot of branching ratio limit. Many experiments are involved, as you can see. It's all the way down, and CMS and LSCB finally nailed it that they've seen this B sub S to mu mu. That shows this number. This is this one with the error. Standard model here is here. B0 to mu mu, there's upper bound, but not yet observed, but that error bar shows here. And that can be compared with various new physics models. But we always hope that this number is somewhere away from standard model. But again, standard model looks quite good. So other B sub B decaying to S mu mu from B0 to K star 0, mu plus, mu minus. All 3 experiments have seen the resonances in this channel. However, that LSCB, there's some deviation for some of their parameters that up to 3.7 sigma. LSCB also looked at B plus decaying to K plus and mu mu over K to EE. So checking this lepton universality, they see about 2.5 sigma deviation from standard model. There are other measurements from Baba and Bell. They are agreeing with the standard model, but their uncertainties are much larger than LSCB. But again, more data will tell us whether something really going on with statistical fluctuation. Now, all these CKM matrices and angles and size, there are new results from Bell, and also LSCB now joined the CP violation game. So here the issues or questions are all the angle measurements, whether that's agreeing with the side measurements, or this loop decay and the treat level decays, whether the results are consistent or not. So here are the global fits. So bottom line is everything goes here very well. So the agreement is extremely good for all different measurements, except about 1.5 sigma deviation for our ring here coming from VUB. It's not big discrepancy, but there was some tension. If you turning this into a sort of how much of new physics might be needed, so at the level of a 10 or 20% new physics amplitude in the B sub D mixing is perfectly compatible with all current data. Now, phase of a VTS, 2 ways, B sub S bar mixing. Here are all the Tevatron and LSC results. These are combined very well, agreeing with the standard model again. CMS was not included here. They just have this new result at ICHEP. This 68% country is a red one, and this combined, the one is a gray. So again, very well agreement with standard model. Penguin B sub S decays. There are beautiful measurements, list of measurements there. They're all happily agreeing with the standard model. And B plus to tau and tau neutrino decay. This is sensitive to new physics like Charles Higgs. The Bell, the experiment is searching for that. This is the area that's very complementary between B factories and LSC. The one news about the KEC-B, there's a big upgrade going on from Super KEC-B, KEC-B to Super KEC-B. They start online sometime 2017, 2018 or so. With KEC-B, new accelerator, huge luminosity the upgrade or improvement, and new detector upgrade, detector Bell 2, and the LSCB upgrade, again, machine and detector upgrade. The list of all the physics can be done is extremely rich, and again, we really look forward to seeing beautiful results in the future. There are 2 future K-on programs coming online very soon. One is the NH62 ESRN. This is K plus decaying to pi plus nu, starting about this fall. So within a couple of years, they'll get about 100 events. That means the statistical error is about 3%. Koto in Japan, this is the K long to pi 0 nu. This is a very, very hard experiment with a couple of years of data taking. They expect a few events. So that one, if standard model predicted somewhere here, this is excluded by theory, and this is excluded by previous experiments. So these are the allowed reason. then you can compare with the various new models. So it's interesting to see where it happens there. There's also the experiment called OKA at U70 Protvino in Russia. That's measuring KE3 and future number of channels will be measured. And Chloe is upgrading its detector and Daphne, and the commissioning is undergoing now. Now moving to muons, first of all, muon 2E gamma. So this channel in standard model branching ratio is less than 10 to the minus 50, so this is forget it, it's impossible. But interestingly, various kind of SUSY models will enhance almost like 35 orders of magnitude higher branching ratio. So with the current experiments, there's a possibility of seeing that. So mu2e gamma, their current limit is 5.7 times 10 to the 13. And now they are upgrading and they start taking data again next year, getting another order of magnitude better sensitivity. So this is a plot of a new physics scale in TeV, 1,000 and 10,000 TeV versus a different kind of physics model. This side is a more contact interaction new model, and this side is a more dipole or the SUSY like the interactions showing here. So mu2e gamma experiments right now is somewhere here excluded. Future will go here. The other experiment is mu2e conversion in the field of nucleus. That one actually sensitive, both areas are even more sensitive to this type of the contact interactions, so they are quite complementary to each other. So there are a suite of experiments going on. JPARC, Japanese program, there are very relatively kind of easy, relatively easy, not easy, the sensitivity to really hard ones, so starting from 10 to the minus 14, and COMET phase 1, 10 to the minus 14, 15, and phase 2, 6 times 10 to the minus 17. From the mu2e, starting similar time is a COMET phase 2, it has also similar sensitivity. With that, the sensitivity goes to almost the much more than 1,000 TeV in all different kind of interactions. So for muon G-2 experiment a number of times, this topic raised in this conference, there are 2 experiments it's going on, well, actually not going on, at least one experiment under construction that's at Fermilab. JPARC, I believe, is also will construct different kind of technology. Just to show you where we are, this is the current Brookhaven measurements, and this is a theory predictions that discrepancy is over 3 sigma-ish, and that new measurements will become as narrow as that red line. For the electroweaks, the precision measurements at low energy, the weak mixing angle, this ongoing experiments, the error bar will be something like that, and proposed one, you'll see that how small that is. This is also very sensitive to new physics. So I'm not going to say anything about enabling technology because we just heard the importance of accelerators and detectors, instrumentation, and computing. Everything that I said can't be done without this, the enabling technology. It's a very important one. Similarly, outreach and education is very important, and I'm not going to cover here. So in conclusion, as I mentioned, the particle physics questions are compelling and difficult and intertwined, and it requires multiple approaches. And we've seen in this conference that there are many different type of experiments are done and results were presented. Unfortunately, standard model still works very well. I hope it won't like that for long. We heard that there are a broad spectrum of new the upgraded experiments, upgraded accelerators, or new experiments are coming soon. So we have an incredible hope that we'll break the standard model. So at the next ICHEP meeting, first of all, this one said January 2016 in Zurich, Switzerland. As you heard from Andre, this is a fake, so this is not the one. So don't pay any registration fee there. Your money will just disappear. Now, this one shows Paris, France. We had a Paris 2010 ICHEP. I don't know, they are doing again. It's a September, late September 2016. And this is wrong too, don't pay anything. what about, oops. Okay, what about this one? 2016, Chicago. Looks very, how do I say, dull, but it's not colorful. I guess that's like us. So, well, we'll make it better, believe me. This is a sort of space holder. Yes, this is a real one, and it will be August 3rd to August 10th in Chicago, downtown Chicago. So this is a beautiful Lake Michigan. The hotel is somewhere here and looks like that. Chicago River runs like this, and then around the other side is lake. This is near museum campus, beautiful parks, and there are free concerts with the world-class music and dance and all sort of things, beach. There's also for family museum park. It's not far away from the airport. It's about 25 minutes or 20 to 25 minutes if there's no traffic from O'Hare Airport, or 20 minutes from Midway. This also will have this primary hotel for participants, although you can stay nearby hotels, but we'll have 500 rooms booked already. So in that conference, I really hope that we'll crack standard model. I have a number of reasons to believe that. Firstly, LSC start running next year at much higher energy and higher luminosity, so 2016 is the best time to bring new discoveries. Neutrino T2K would collect a lot of data. NOVA just started, so in a couple of years or so, we'll have a quite chunk of data. We may have a better information about CP phase or mass hierarchy. Reactor neutrino experiments, I'm sure that they have another juicy story to tell us. Anomalies or stellar neutrinos with the microme detector, etc. We'll have some information, hopefully. Also, the kaon experiment, the Cotton and Na62 start running soon, so I hope there are some results. Dark matter is very, very active. Something might happen very soon. That's my feeling. Dark energy DS, 2 years of data taking, they will bring first dark energy results. And by SEP2 Planck, we'll have some conclusion from there, and hopefully something unexpected. But also, I hope that like what we did this time, we get together again, think about globally, as a whole international community together, think about our strategic plan. And if we discover something there, we have to think about what that means in terms of our future directions. So this conference has been extremely well done and remarkable success, as Victor said earlier. Of course, this thanks to Juan and Manuel and all the entire team. Muchas gracias. Thank you.
Thank you very much, Professor Kim, for your beautiful and colorful talk. So we have time maybe for 2 short questions, please. Do you have any? Oh, okay. Oh, please.
Answer is no, Young-Kee.
Microphone, please.
Not the details, but your last slide, hoping to crack in the standard model. I think most of neutrino physicists believe that we have that already, probably not very visible. There's thin crack in the standard model.
Yeah, I mean,
as well as there's a dark matter and a dark energy. Yeah. So I think we don't have, something concretely to write down, but there is neutrino part, and then dark matter, dark energy. There's
right. Yeah. So that's I already.
I just want to make sure that a lot of people know that.
That's right. What I meant is that, let's say dark matter, we know that it doesn't, standard model doesn't work, but until we find something more, that's what I meant. But certainly you are correct. The answer is yes.
Any more question? Let's thank speaker again.